In this section, I'm going to be discussing various types of mappings, such as functions, sequences, system operators, and transforms. On this slide, I need to introduce some notation and terminology that relates to sets. So first of all, as a matter of terminology, a rational number is a number of the form x divided by y, where x and y are integers and y is not equal to 0. In other words, a rational number is simply a ratio of integers. So for example, numbers like minus 5/3, 17/11, 0 are examples of rational numbers. Whereas numbers like pi and e, these are irrational numbers because you can't actually represent them exactly as a ratio of integers. As a matter of notation, there's some symbols that are frequently used for some of the common sets that we often use. So often we use sets of the sets of integers, real numbers, complex numbers, and rational numbers. So these are denoted by Z, R, C, and Q respectively. Since we often deal with intervals on the real line, in other words ranges of real numbers between two values, it's convenient to have a notation for denoting intervals. So on this slide I'm going to introduce some notation in this regard. So for two real numbers a and b, we have various different notations that are indicated here. So this notation, this first one here where we have a and b in square brackets, this denotes all real numbers between a and b, including a and including b. In other words, kind of in terms of formal set notation, we have all x that are real numbers such that a is less than or equal to x, less than or equal to b. In other words, it's all values between a and b, including a and including b. This notation here where we have round brackets around the a and the b, the only difference is that the endpoints of the interval aren't included. So this notation here denotes all values, real values, between a and b, but not including a and not including b. And then we have two other combinations of things where we sort of mix square brackets with round brackets. This next one here where we have square bracket a and b and then round bracket, this is all values between a and b, real values between a and b, including a but not including b. And then the last one is all real numbers between a and b, not including a but including b. So you can see there's a pattern here. Essentially the square bracket going along with an endpoint of an interval denotes that that endpoint is included, and a round bracket that goes with an endpoint of the interval indicates that endpoint is not included. So just as some additional examples, if we write something like this, square bracket 0, 100, end square bracket, this denotes all real numbers from 0 to 100, including both 0 and 100. If we write something like this, like a round bracket minus pi, pi square bracket, this denotes all real numbers between minus pi and pi, not including minus pi, but including pi. And then lastly, if we have something like this notation here, this is denoting all real numbers between minus pi and pi, including minus pi, but not including pi. Again, the square bracket means the endpoint is included, the round bracket means that the endpoint's not included. And this just gives us a very convenient way to write intervals, because writing something like this, for example, is much less writing than writing something like what's over here. Next, I need to introduce the concept of a mapping. Now, I'm sure anyone watching this video has already talked about mappings in some earlier math course that they've taken. But I suspect it may be sufficiently long ago that it's been long since forgotten, and since this is kind of important, it's probably worthwhile to kind of quickly review some of the terminology. So a mapping is a relationship involving two sets that associates each element in one set, called the domain, with an element from the other set, which is called the codomain. So in terms of notation, the way we denote a mapping, if we have a mapping called F, we use notation like this. This means that F is a mapping, and it maps elements from the set A, which is the domain, to elements of the set B, which is the codomain. And probably this is best illustrated in terms of an example. So suppose that we have a mapping F, which maps elements in the set A to elements in the set B. So A is the domain, B is the codomain. And suppose A is the set of integers 1, 2, 3, 4, and suppose B is the set of integers 0, 1, 2, 3. And then the mapping F is defined by this equation here. So in terms of the picture, we have the set A, which is the domain, which are the integers 1, 2, 3, 4, and we have the codomain B, which is the integers 0, 1, 2, 3. And then essentially the mapping is represented by the arrows in this diagram. For each element in the set A, it maps to some element in the set B, and the arrow is showing which element in the set B a particular element in the set A maps to. So for example, the element 1 in the set A gets mapped by the mapping F to the element 0 in set B. And you can see this from the equation here, right? So if we take the element 1 from the set A and plug it in for x, so set x equal to 1, if x is 1, then the value of this function is going to be 0. In other words, the value 1 gets mapped to the value 0 in the other set. And just as another example, for example, if we take 3, the element 3 in the set A, this maps to the element 2 in the set B, which you can see from this equation here. If we plug in 3 for x, if x is 3, then the value that we get from this mapping is 2. So it maps the value 3 to the value 2. Now there are many different types of mappings that exist in mathematics, but the types that are most relevant to our study in signals and systems are functions, which I'm sure everyone's had many dealings with already, sequences, which I'm also sure everyone's had many dealings with already, and then system operators and transforms, which are likely to be new, but we'll get to them shortly. Now I'm sure anyone watching this video is already quite well acquainted with the concept of a function. Nevertheless, I think it's quite helpful to go through and formalize some of the terminology and notation that relates to functions, because sometimes it leads to misunderstandings. So first of all, a function is a mapping where the domain is a set that's continuous in nature. So what I mean by this is a set where the elements vary over a continuum. An example would be something like the real numbers, where a real number can take on the value 0, for example. It can take on the value 1. But very importantly, it can take on values over a continuum between 0 and 1. And complex numbers are similar. They can take on values over a continuum. In practice, the codomain for functions is usually either the real numbers or complex numbers. Again, the codomain you can think of as the output for the function. The function, or mapping it, produces values that are in some set, and this is what we call the codomain. Functions are also commonly referred to as continuous time signals, as we saw earlier. And just to give an example, if we write things in math speak, we can say something like what's given here. This is like a little bit of math speak, but if we kind of deconstruct what it's saying f is a mapping. In particular, we're talking about a mapping that's a function, which maps elements from the set of real numbers R to elements of the set R, which is the real numbers. And it's defined by this equation here. So you can see this is just a squaring function. The value that it takes in, it's just squaring it to produce its output. So t is an element from the domain R, so t is a real number, and then the output of the function, you can think of it like the output more formally, it's sort of an element of the codomain, is also a real number as well. Now one thing I want to note here, which is important, it's something that's often a source of misunderstanding, and this is because there's a very prevalent abuse of mathematical notation amongst engineers. The important thing I want to note here is f is the name of the function. F of t is not the name of the function. F of t is a number, it is not a function. And it may seem I'm being a little bit pedantic about notation, but it is important because this raises issues that cause many common misunderstandings among students from what I've seen teaching this course material many times. Just by itself, writing f of t to represent the function in sort of trivial situations, it's not likely to cause misunderstandings, but there's a lot of math in this course where referring to something like this as a function actually will cause a lot of confusion and problems and other things. So try to always make a clear distinction between the name of the function, like the actual function itself, versus evaluating the function at a point. Because this expression here, what you're doing is you're taking the function f, you're evaluating it at point t, where t is a placeholder for some number. T is just a number, right? T is a variable that represents a number. So you're giving the number t to the function f, and it's going to spit out another number. So f of t represents a number. And then lastly, I just want to comment that in this course, mostly we're dealing with functions that are functions of a single variable. In other words, what we referred to as one-dimensional functions earlier. At this point, I'd like to consider an example. In particular, I'd like to consider example 2.2. Example 2.2 has a number of examples of using notation related to functions, which is probably helpful to look at. So suppose we have two functions. One of them is called x1, one of them is called x2. And now consider the expression x1 plus x2. What this denotes is it denotes a function which is formed by summing the functions x1 and x2. To contrast this, if we write an expression that looks something like this, this is a number. In particular, it's the number that we get if we first add the functions x1 and x2. This gives us a new function, which is the sum of x1 and x2. And then we evaluate that function at the point t, which gives us a number. Now, since the addition of functions is defined pointwise, in other words, the way that we define the addition of functions, in other words, if I have a function x1 and x2 and I add them, if we ignore the t here, just the first set of brackets, what's inside the first set of brackets here is just a function, which is the sum of the functions x1 and x2, and then we're evaluating that function at t. And on the right-hand side here, we have the function x1 evaluated at t added to the function x2 evaluated at t. Now the left-hand side and right-hand side are always equal. The reason why is the way that we define the addition of functions, in other words, what the meaning of x1 plus x2 is, it's defined by an equation like this. The way that we add functions is we add them at every single pair of points. In other words, addition is defined pointwise for functions. And it's the same story for subtraction, multiplication, and division. Again, there's subtle differences between the left and right-hand side of each of these equations, just like in the equation above. On the left-hand side here, for example, we're subtracting the function x1 and x2. So we're subtracting functions. And then we get a new function, which we're evaluating at t. On the right-hand side here, we're evaluating the function x1 at t. That gives us a number. Then we're evaluating the function x2 at t. This gives us another number, and then we're subtracting those numbers. So on the one side, we're subtracting functions. On the other side of the equation, we're subtracting numbers. But these things are always equal. The reason why is this is how we define subtraction of functions. In other words, the way that we define the subtraction of functions in this way is in terms of subtracting the functions pointwise. And similarly for multiplication and division. And I think probably most students don't have too much difficulty with this. Something that sometimes causes problems, though, is that because most or maybe all mathematical operations that students have typically dealt with before taking this course are always things that can be defined pointwise, they just take for granted that you can kind of, whether you write the expression on the left-hand side of the equation or the expression on the right-hand side, it doesn't really matter because they're just always the same. This is true for the basic arithmetic operations like adding, subtracting, multiplying, and dividing, but there are some mathematical operations that fundamentally only can be applied to functions. And one of them that we'll look at later in the course is called convolution. So the subtlety here is we have to be a little bit careful if we start taking expressions like this where the operation, so here this kind of diamond shape is just representing some particular operation that we're not specifying what it is, but suppose that it is only defined, it can't be defined pointwise, it only can be defined between two functions. In this case, an expression like this would be valid because here the operands of this particular operator that we've denoted by diamond are two functions. We're giving it two functions, so if this is an operation that can only be applied to functions, not to numbers, we're okay because here we're applying it to functions. But on the other hand, if we try to write an expression like this has no meaning, because if the operation, this diamond shape, represents an operation that can't be defined pointwise, it can only be defined to operate on functions themselves, this expression doesn't make any sense because x1 of t is a number, x2 of t is a number, because we're evaluating the function x1 at t, this gives us a number. We're evaluating x2 at t, this gives us another number, and then we're trying to apply this operation that's designated by this diamond shape with two numbers. But if this diamond shape operator only can be applied to functions, this expression doesn't make any sense. So later on in the course, we'll learn of something called convolution. It's not denoted by this diamond shape, but rather it's denoted by a star symbol. And this is an operation that's only defined between functions. It's not defined between numbers. So if in the case of convolution, for example, where the symbol diamond would be replaced by a star, because again that's the symbol that we use for convolution, an expression like this is perfectly valid. We can convolve two functions, but an expression like this would not be valid because we can't convolve numbers. Anyway, this will probably make a little bit more sense, this last little part, once we've talked about convolution a bit later in the course. But I just want to point this out because this causes a lot of headaches for a lot of students, the fact that some mathematical operations involving functions cannot be defined pointwise, and therefore you can't start writing notation like this. And unfortunately, a lot of engineering textbooks abuse mathematical notation. They write stuff like this, and it always causes confusion for students in my experience. So I'm trying to avoid this and kind of be a little bit more pedantic about notation to try to save students a little bit of headaches. Anyway, I guess enough said about this. Now I'm sure anyone watching this video is already quite well acquainted with the concept of a sequence. Nevertheless, it's still quite helpful to go through and formalize some of the terminology and notation that relates to sequences. So first of all, a sequence is a mapping where the domain is a set that's discrete in nature, such as the integers or a subset of the integers. And what makes the integers discrete is that, for example, an integer can take on the value 0, it can take on the value 1, but it importantly can't take on values over a continuum between 0 and 1. In other words, it can only take on certain prescribed values. In practice, the codomain for a sequence is typically either the real numbers or complex numbers, at least in the context of math relating to signals and systems. In other words, sequences are normally either real valued or complex valued. Sequences are also commonly referred to as discrete time signals, as we saw earlier. Now what I'd like to do next is introduce some formal notation that relates to sequences. So first of all, let's use the symbol z with a superscript plus to denote the set of strictly positive integers, in other words the integers 1, 2, 3, 4, and so on, which are sometimes referred to as the natural numbers. And what I want to do is look at this notation here for defining a sequence. It's kind of more formal. I'm going to go through and deconstruct it. So first of all, we're saying that f is a mapping. So f is basically a mapping that's a sequence here. And it maps the domain, which is the set of positive integers, to the codomain, which is the set of positive integers. And the equation that defines this sequence is f of n is equal to n squared. In other words, the sequence is just a sequence of perfect squares. 1 squared, 2 squared, 3 squared, and so on. Now I want to make one important comment with respect to notation. The expression f denotes a sequence, whereas the expression f of n denotes a number. F of n is a number because what this notation means is we're taking the sequence f and we're evaluating it at the point n, which gives us a number. It's whatever the sequence is equal to at this point n. And the reason why I'm pointing this out is that often engineers abuse mathematical notation and they write an expression like this, f of n, meaning a function, and this is not really correct. And in some cases it's kind of a harmless thing to do. In other words, in trivial cases, abusing the notation and using f of n to denote the sequence f rather than the value of the sequence f at n, sometimes this is harmless to do. But there are a lot of situations where it's really important to make a distinction, and in the context of this course in the mathematics of signals and systems, there are a lot of places where if you start mixing up sequences and the value of a sequence evaluated at a point, in other words, if you start mixing up expressions like this one and this one, it can get you into a lot of trouble. So it's always a good idea to try to keep very clear in your mind and distinguish in the notation that you write a sequence versus the sequence evaluated at a point. Now, as a matter of notation, if we want to denote the nth element of a sequence, we can denote it either using notation like this, which is what's used above, or equivalently we can just write the name of the sequence with a subscript n. And then lastly, I just want to comment that in this particular course we'll be focusing primarily on sequences that have a single independent variable. In other words, there's a single index value or point at which we're evaluating the sequence. The next type of mapping that I need to introduce is what is known as a system operator. So a system operator is essentially the mathematical abstraction that we use to represent a system. In other words, the way that we represent systems mathematically is in terms of what's called a system operator. Now, in the context of this course, we focus almost exclusively on the case of single input, single output systems, so I'm going to focus on this case here. So a single input, single output system operator maps a function or sequence, which represents the input to the system, to another function or sequence, which represents the output of the system. Now, unlike the case of functions or sequences, system operators do not map numbers to numbers. Rather, a system operator maps functions or sequences to functions or sequences. In other words, system operators deal in functions and sequences, not numbers. Now I want to go through an example just to illustrate some of the formal notation which relates to system operators. So first of all, let's use f to denote the set of functions that map real numbers to real numbers. So basically f is a set of functions whose domain and codomain are the real numbers. And what I want to do is I want to formally define a mapping called h that corresponds to a system operator. We can do this using notation like this. And I just want to go through and deconstruct what the notation is saying. So essentially what this notation is saying is we have a mapping called h, but this mapping that we're introducing here specifically is a system operator type of mapping. It maps elements from the domain f, which is a set of functions, to the codomain f, which is a set of functions that we were just introduced to a moment ago. And the equation that defines this particular operator or mapping is this equation here. So essentially what this is saying is that if we look at kind of individual pieces of this equation, hx corresponds to the output of the system when we put the function x into the system. And then the entire left-hand side of this equation, what we have is the output of the system evaluated at the point t. The output of the system when the input is x specifically. And then the right-hand side is just saying what the value of this output is at the point in time t. And what you can see here is effectively the output of the system, which is given by hx, is just 2 times the input to the system. So this particular system here is just an amplifier which produces an output which is 2 times its input. In other words, it's amplifying by a factor of 2. And just as a matter of notation, hx denotes a function, not a number. This is important to understand because system operators map functions or sequences to functions or sequences. So when we give the system operator h, a function in this case, it doesn't give us back a number, it gives us back a whole function. At this point, I need to make some comments about operator notation for continuous time systems. So suppose that we have a system operator h and a function x. Then in terms of notation, hx corresponds to the function that's produced as the output of the system when the input is the function x. In other words, the operand that we're providing to this operator, the x, is the input to the system, and then hx represents the output of the system when the input is x. In other words, hx is a function. Now often when we're using operator notation, we tend to drop parentheses and brackets when we don't really need them for grouping purposes. So for example, although we could write h of x like this to denote the output of the system when the input is x, we could instead just write hx. Because there's really only one way that you could group things in this expression, because there's only a single other thing other than the h, so really this is the only way that you could interpret the expression. So for this reason we can just drop the parentheses. And for example, we could write an expression like this to denote the this part here of the expression is the output that's produced when the input is x. And then we're taking that function and we're evaluating it at t. So this overall expression here is the function evaluated at t, where the function involved is the output of the system when the input is x. Now instead of writing this expression here, we could simply drop the first set of brackets and write this. And the reason why we can do this wouldn't introduce any ambiguity, because this is the only reasonable way to interpret this expression over here. The reason why is the only other way we could group the operations that are happening here other than this expression here will be the expression that's shown here. But this is not a mathematically valid expression, because here The thing that we're giving to h as an operand, in other words, the thing in the square brackets here, is a number. It's not a function, because remember, x of t denotes the value of the function x evaluated at t, which is a number. It's not a function. And system operators always take as an operand a function. So this expression here doesn't make any sense, because we're trying to give a number to a system operator, which doesn't make any sense. So for this reason, we can drop the brackets around the x here, because it doesn't introduce any ambiguity. There's only one reasonable way to interpret this expression. So again, I want to just emphasize hx is a function, and hx of t is a number. In particular, hx corresponds to the function that's produced when the input to the system is x. And then hx of t, this expression here, if we just kind of break it down into its individual pieces, hx is a function. It's the output that we get when we put x into the system. And because hx is a function, we can evaluate it at a point. So what we're doing is we're taking this function hx, and then we're evaluating it at the point t. But this gives us a number. Now sometimes we can't drop brackets that are associated with operator notation because they are actually needed for grouping. So just to give an example of this, if we're writing an expression like what's shown here, we can't drop the brackets in this expression. This will change the meaning because what the left-hand side of this equation or expression is saying is that we're computing the sum of the functions x1 and x2, and then we're putting that sum into the system h. And the output that we get is this overall expression here. On the right-hand side, though, if we drop the brackets, what this is saying is we give the function x1 to the system h, and then we observe what the output is. So in other words, hx1 corresponds to the output produced when the input is x1. And then once we have that output, we simply add x2 to it. So the left and right-hand sides are different. So it's important in an example like this to include the brackets. We can't drop them. So you can't always start dropping brackets all over the place when you're using operator notation. Sometimes they are necessary for grouping. The last comment I want to make here is when there's multiple operators involved in some kind of mathematical expression, they group from right to left. So for example, if we write an expression like this, h2, h1x, where h2 is a system operator and h1 is a system operator, the implied brackets or grouping is what's shown here. So in other words, we first take h1 and we apply it to x. So we're basically taking x, putting it into the system which is represented by the operator h1, and then this will produce an output which is denoted by h1 of x. And h1 of x itself is a function. It's the output that was produced by some system. And then what we're doing is we're taking this function h1 of x and we're putting it into the system represented by the operator h2. And then this whole expression here corresponds to the output that we get from the system whose system operator is h2. So at this point I'd like to consider a few examples. So first of all, I'd like to consider example 2.6. In this example we have a system operator h, a function x, a real variable t, and a real constant t0. And what we want to do is contemplate the meaning of this highlighted expression here. So hx of t minus t0, what does this mean? Well, let's break this expression down into the individual pieces that make it up. So h is just denoting a system operator. So in terms of a picture, we have something like this. We have some system which is represented by the operator h, which has some input and some output. Then if we focus on the hx part of the expression, hx is by definition the output of the system when the input is the function x. So in terms of a picture, we have something that looks like this, where we have our system, which is represented by the operator h. The input that we're putting into the system is the function x, and by definition the output of the system is just hx. So hx denotes the output of the system when the input is x. Now since hx is a function, we can evaluate it at a point. So the expression hx of t minus t0, what this means is we're taking the function hx, which is this output of the system when the input is x, and we're evaluating that function at t minus t0. So this is the meaning of the expression hx of t minus t0. We're effectively taking the function x, putting it into the system that's represented by the operator h, and this gives us the output, which is denoted by hx, and then we're taking that function hx and we're evaluating it at t minus t naught. The second example I'd like to look at is example 2.7. In this example, we're given an operator h, a function x prime, and a real number t. And what we want to do is we want to contemplate the meaning of this mathematical expression here, hx prime of t. In other words, what does it mean? So let's take this expression and break it down into its constituent parts. So first of all, if we just focus on h is just an operator that represents a system. So in terms of a picture, we have something that looks like this. We have our system, which is denoted by the operator h, with some input and some output. Then if we look at hx prime, this part of the expression, so hx prime is simply the output of the system when the input to the system is the function x prime. So in terms of a picture, we have something that looks like this. We have our system, which is denoted by the operator h. The input is the function x prime, and by definition, the output is just hx prime. Now, since hx prime is a function, we can evaluate it at a point. So we can, for example, evaluate this function at the point t. So hx prime of t, which is the expression that we're trying to figure out what its meaning is, it's simply this function hx prime evaluated at t, where in particular the function hx prime is the output of the system, which is denoted by this operator h, when the input to the system is the function x prime. Another type of mappings that I need to comment on are what are known as transforms. So later in the course we'll be introduced to a number of types of transforms. In the context of this course, transforms have a mathematical structure which is very similar to system operators. In other words, in the context of this course, transforms are operators that map functions or sequences to functions or sequences. Because the transforms that we look at in this course have a very similar structure to system operators, many of the comments that I made earlier about system operators apply in the case of transforms. For example, later in the course we'll talk about something called the Fourier transform, and this is denoted by the letter f. So this is an operator that can be applied to either a function or a sequence. So if we have a function or sequence x, we can apply this operator f to it, and it turns out in both cases this gives us a function as a result. Anyway, we'll look at the Fourier transform in much more detail later in the course. Some examples of transforms that we consider in the study of signals and systems are listed on the next slide, so I'll make a few comments about them in a moment. This slide lists a number of transforms that are of fundamental importance in the study of signals and systems. In this course, we're going to focus on the first three in considerable detail. We'll be talking about continuous time Fourier series, the continuous time Fourier transform, and the Laplace transform. And you can see here these transforms have different domains and codomains. Sometimes they're functions, sometimes they're sequences, sometimes they're periodic functions, and in some cases the functions are defined on the real numbers, sometimes they're defined on the complex numbers, and sometimes we have sequences which are defined on the integers. Anyway, this is all I have to say about these transforms now, but we'll be looking at them in considerable detail later in the course.